Okay, so this is the second technical talk in this NAG lecture series. Nikita will be talking about Yang-Mills theory on origami world sheets and polymer in three-dimensional gravity.
Thank you. So, so this is the kind of the fifth short story of gauge theory revealing itself in maybe more conventional physics settings, but the origin and the origin of the story is kind of old, and it's something which I didn't work for a long time on. I just had a few thoughts maybe a couple of years ago, never published yet, but somehow it feels it might be important. So you'll be the judge. Okay, so but the setting is something which some of you are familiar with. So we'll be talking about classical and quantum integrable systems, which are related to gauge theories. And the starting point would be the two-dimensional Mills theory and three-dimensional Chern-Simons theory, and a little bit of three-dimensional gravity, which, for the purposes of this talk, is a kind of version of three-dimensional Chern-Simons theory. So let's start with something very simple: 2D Yang-Mills. We spoke a little bit about it in previous lectures, but let me just remind you. Of course, if you write the action of 2D Yang-Mills in the kind of general form, it looks as scary as it is in 4 dimensions. But if you rewrite it in the first order formalism, you realize that this action actually depends on very few geometric structures on space-time, which is two-dimensional surface. So as I said, if we go to the first order formalism, we introduce a kind of auxiliary field E, which takes values in the Lie algebra. It's a scalar on the worldsheet. It is called the electric field. To write the Lagrangian, so the first term is just a trace of E times the curvature. So curvature is a two-form, so you don't need anything else to integrate over the worldsheet. And for the second term, you have trace E squared, which is a scalar, so you need a two-form to write the Lagrangian density. So unlike the Yang-Mills theory in higher dimensions, which depends on actual metric on spacetime, this two-dimensional version does not care about the metric on the worldsheet. It only cares about the topology and the choice of the volume form. And there is a theorem by Jürgen Moser a long time ago, which says that in 2 dimensions, any two symplectic forms. So volume form is like a symplectic form is something which doesn't vanish. Two form doesn't vanish. So any two volume forms can be mapped to each other by diffeomorphism, as long as the total area of these two forms agrees. So essentially, apart from the topology of sigma, there is only one invariant, which is the total area. And so in that sense, this theory is almost a topological field theory. There is no local structure to this volume form, which you can capture. But now, we can anticipate that the theory will be simple. But let's do the kind of canonical analysis of this theory. Let's take the sigma to be a cylinder, so a product of a circle times a line. And so if you look at the Lagrangian, which is written here, this first term is essentially the PDQ term in the canonical classical mechanical approach. The second term corresponds to the Hamiltonian. And so the first term is, so E is canonically conjugate to A, the space component of the gauge field. There is another component of the gauge field which is long time, but as usual in gauge theory, it enters the Lagrangian without time derivatives. So it acts as a Lagrange multiplier or constraint. And so this constraint is what essentially performs the symplectic reduction or symplectic quotient of the phase space, which is the space of pairs, a gauge field on the circle and the electric field, modulo the action of the gauge group. So the reduction, so these two lines means that that we impose the Gauss law and divide by the action of the group. And that leads to something finite dimensional. So the phase space is actually finite dimensional. It's the quotient of the cotangent bundle to the maximal torus of the gauge group by the action of the Weyl group. And so the Hamiltonian, which was trace E squared, actually trace E squared integrate over the spatial manifold, becomes upon quantization just a Laplacian acting on the W invariant functions on the maximal torus. And so this is how it's done in more detail. So there is a moment map for the gauge group action, also known as the Gauss law. Setting it to 0, we conclude that the electric field is covariantly constant. So up to some gauge transformation, it is actually constant along space. And the maximal torus comes from the eigenvalues, the conjugacy class of the holonomy of the gauge field around the space circle. And so that's how you arrive at this conclusion. So now, so this was very, very simple. I'm going to tell you about something which is a little bit trickier, more complicated, more interesting, and recently meaning in the last 50 years, in the last 35 years, which was kind of getting into the realm of gauge theories. But originally it was something very abstract, invented by Nigel Hitchen. And so it's called Hitchin system. This is an interesting classical mechanical system, generalized in the sense that everything is complex in this generalization. So the phase space is complex and the Hamiltonians are complex. So the data for his system is a choice of a complex curve. So one complex dimensional, two real dimensional surface of some genus G, choice of a Lie group and its complex version. And so the phase space of that guy is the moduli space of pairs. In gauge theory language, so the pairs would be the 0-1 form, 0-1 part of the gauge field on C, and 1-0 form valued in adjoint representation. So it is sort of similar to what we had for the Young-Mills theory, but now imagine that I replaced the circle, the one real dimensional space, by one complex dimensional space. And now the gauge field, so the gauge field had only one component along the circle. In 2 dimensions, it has 2 components, but if I choose a complex structure, then I can single out one of these components, and this is what I want to look at, the antiholomorphic component. But now what used to be the electric field, which was a scalar, now I need to be able to pair it with this component of the gauge field. And so Hitchen's idea was that let's take it to be not a scalar function, but a 1 form, 1-0 form. So then these two guys are canonically conjugate. And so then we can perform this similar reduction to what we had in Young-Mills case, but now things happen in 2 dimensions. So so the gauge group acts on these pairs in this way. So AZ bar transforms as a gauge field, and phi transforms as a Higgs field, adjoint valued Higgs field. And the Gauss law is now, it's a 2 form in 2 dimensions, but the formula locally is the same. So it's just a covariant derivative of the scalar. But now it's twisted. So this is the reduction which preserves the symplexic form, which is now holomorphic. Holomorphic in the sense that phi and AZ bar are all complex. Yeah, I know. And I'm not looking at the complex conjugates. So remarkably, well, as in previous case, even though we started with infinite dimensional space of gauge fields and these twisted scalars, performing the reduction with respect to gauge group gives you something finite dimensional. And this is now something which is kind of intricately depends on the topology of C, and also on the complex structure. So what Hitchen observed was that the result is actually not just a phase space, abstract phase space, but it's a phase space with a maximal set of commuting Hamiltonians. So these Hamiltonians you get by taking invariant polynomials on the Lie algebra, and there is some vector space of such polynomials. They come in, so you can choose a basis of homogeneous polynomials of certain degrees, and so these degrees are kind of invariants of the Lie algebra. So for SUN, those degrees would be 2, 3, 4 up to n. So these are just the degrees of Casimirs in other language. For SUN, the simplest invariant will be trace phi squared, so it's quadratic. Next one will be trace phi cubed, and up to trace phi 10. So if I take this polynomial and substitute in it the field phi, because phi is actually one form, 1-0 form, this guy will be kind of a dk, 0 differential on C. Sorry, this was C sigma. So I need to make it into a density which I can integrate. I need to multiply it by this differential of degrees 1 minus d, 1. So this it might look unfamiliar, but if d is equal to 2, then this is minus 1 differential, which we know under the name of Beltrami differentials. And so these guys are kind of generalized Beltrami differentials. So they describe the for d equals 2, they describe the variations of complex structure, and for high g, they describe what is called the variations of W structure, generalizations of complex structure. Now, because these functions were constructed out of phi without using a, they Poisson commute by construction. So they commute. What is slightly non-trivial, and it's a remarkable identity, is that the total number of independent such functions is precisely equal to half of dimension of the space. So that uses a little bit of knowledge of the relation of these degrees to the dimension of the group. So there's this identity, I believe, due to constant, or maybe the simplest proof is due to constant. So constant showed that you can always choose an SL2 subgroup of subalgebra of the Lie algebra of the group G, such that the adjoint representation of the group will decompose into the E-reps of this SL2, and the spins of those E-reps will be dk minus 1. So this number 2d minus 1 is actually 2j plus 1 when j is d minus 1. I think it's a principal embedding. Yes. So for SUN, you will just get all even numbers starting with 3. So it's an interesting integrable system. It's a bit unusual. I mean, it was unusual like in 87 when Hitchin introduced it. Maybe it was unusual in the West. For people in Soviet Union, it was not that unusual. They already dealt with these complex systems, but this system was criticized, in particular by Novikov, whom I mentioned in a different context yesterday, because it was too abstract. So there is this construction. It gives you something which is explicitly integrable, but there is no magic. Usually, you are given a Hamiltonian system in some coordinates and with some coordinates and momenta. It looks like a complicated dynamics, and then by some work you show that it actually there are additional Hamiltonians which Poisson commute, and so you can. So there is some achievement. Here there is no achievement. You just given a system which is already kind of action angle variables.
I have one thing. Like, can I understand this Hamiltonian? What kind of transformation that they generate?
Yeah, that's very complicated actually. So of course, so if I do this before the reduction, so my phase space is the space of pairs AZ bar by Z, right? So if I just take the Hamiltonian, which is some polynomial of phi, so what it does, so it doesn't change phi at all, and AZ bar. So if I flow some time, let's say time 1, you can absorb time in a normalization of mu. So that would be just derivative of p. Right. Now, so this is on the infinite dimensional space, right? So then it's obvious that these things commute because phi doesn't change, and so you can put here the sum over k I independently. But now we want to perform a reduction, and so it means that well, first of all, we no longer consider an arbitrary pair of phi and a, but only those for which this relation is satisfied. So obviously, these transformations preserve this relation because az bar is shifted by something which is a function of phi, and the invariance of p, the Casimir nature of p, means precisely that this derivative commutes with phi. So that's it. But then you might want to have some. We're also supposed to caution by the action of the gauge group. So there might be some gauge condition. And so if you have some gauge fixing condition, then these guys should be supplemented by the compensating gauge transformations. Where you adjust G in such a way that as to obey the gauge condition. So then this dynamic becomes non-trivial, quite non-trivial. This G can be connected to the so-called Lux operator. So there is Lux pair. So then, of course, I mean, whenever you try to describe it at some explicit coordinates, it will be a non-trivial dynamics. It's just that Novikov's point was that, well, what kind of coordinates can you use? It's if you are working on compact Riemann surface of high genus, there is no obvious choice of coordinate. So this is where I entered this business. So that was like early 90s of last century. And with the help of my co-author Sasha Gorsky, so we realized that, well, first in one example, and then I kind of generalized it to many examples, that to make things kind of more explicit, you need to add punctures. And so in the language of conformal field theory, which was somehow behind the story, but was not never at the time was not clear, what Hitchin studies corresponds to studying CFT on just some Riemann surface without any insertions. So you could study partition function as a function of some parameters. But if you want to have correlation functions, you insert observables, and so they will they will show up as sources in the Hitchin equation. But so my point of view was that you actually get these things for free if you take Hitchin's definition and then start degenerating the complex structure of the original curve. So if you pinch some handles, then essentially, yeah, the result. If you look at the resulting equations, the limiting equations on one of the components of the resulting surface, you will see these equations. So these delta functions are just the results of having an infinitely long and thin tube coming out. But the outcome of that is now that you can describe the system in more or less explicit coordinates. And it turned out that actually quite famous systems, which were studied by mathematicians for over 100 years, were part of this story. So one of the system is what physicists call the Godin system, but actually mathematicians studied like 100 years before Godin, and it was called Garnier system, also connected to Penlevé equations. So so the underlying curve has genus 0, and you need to have at least 3 punctures to make things interesting, as in CFT. And so in that case, remarkably, the gauge field can be completely gauged away, because in genus 0, you can always find G such that so the AZ bar is always pure gauge. So the Higgs field then becomes just one form with poles. And so it's completely determined by its residues. And so the phase space is just parameterized by the choices of those residues. Now, so these residues take values in the real algebra. But as for scalar one forms, there is a condition that the sum of the residues should be equal to 0. Therefore, this n elements of the real algebra, which are constrained to belong to some adjoint orbits, they sum up to 0, and there is an overall gauge invariance. So the phase space can be described in kind of fine dimensional terms as the complex. Yes. So these are all complex coadjoint orbits, right? So these are, so the phase space is it's a symplectic quotient of the product of adjoint or coadjoint orbits by the diagonal action of the complexified group. How to think of this? So this is where we will approach polymers. Let's work it out in the example of the group SL2C, simplest group. Now these coadjoint orbits are actually very, very simple gadgets in this case. So these are, so any 2x2 traceless matrix with complex entries, you can parameterize in this way, where x, y, and z are complex numbers. Now, when I say that this is an orbit, when I say that I fix the conjugacy class of such a matrix, its conjugacy class means that I'm fixing its eigenvalues. And so these eigenvalues we can compute from, so the trace is 0, so the eigenvalues we can compute from the determinant. So the determinant, why is this parameterization x, y, z is convenient? Because the determinant is just the sum of squares, negative sum of squares. And so fixing the eigenvalues means that I'm fixing the sum of squares of these three numbers. Okay, so now I have a collection of such triples whose sums of squares are fixed. That's the part of my data. And I have a condition that the sum of them is equal to 0. So sum. If these were real numbers, then I could geometrically represent this by saying that, okay, I just need to have a closed polygon whose edges have fixed lengths, nu1, nu2, nu3, nu4, etc. And so my phase space is just the space of such polygons considered up to isometries. So there is no specific point where they start, and the overall SL2C action. So something I should have said, that the adjoint action of SL2C on such a matrix looks like rotation, Euclidean rotation of x, y, and z. Just that instead of the real parameters of the real rotation, you substitute complex parameters. So it's kind of complexified rotations. So this is what I meant. So the condition that the sum is equal to 0 is just that's the condition on these sums. So the phase space is space of closed n-gons in C3 as opposed to R3 with fixed lengths of edges modulo isometry. So you take this gadget and just you rotate it arbitrarily. So that doesn't change the point of the phase. Global rotation. Yes. So if right. So the simplest case would be, I mean, okay. So if there are only 3 of them, if n equals to 3, so this is why I said that I need at least 3 punctures. Well, the 3 edges in real life, you need a triangle inequality. So then in complex life, you don't need any conditions. You can always form a triangle. It's rigid. So there are no invariants. But once you add the 4th guy, so now you have inequivalent quadrangles because now you have some flexibility. So you can rotate around this diagonal or around this diagonal. So there are 2 degrees of freedom. And for the n-gon, we will get something of dimension 2 times n minus 3. So 2 because it's a phase space, so it should be symplectic. and then -3 is the number of.
So these relative motions are not allowed in your isometries, or are
So
they?
this relative
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 between
motions
the edges.
changing. They're actually sorry. Suppose let's.
No, what I'm saying is the kind of configuration change that you showed. That's not part of your isometry. What you call as isometry.
It's not part of the
It's not
isometry.
part of it.
This is actual movement
in the
on
modular
this
space.
on this space.
Right,
Yes,
right.
yes.
Okay.
So this when I did that, I passed from one point on the phase space to another point on the phase space. Okay. So that was one example, one way of making the system kind of explicit. Another way was to go to genus 1 with one puncture and one, so choosing a so-called minimal orbit attached to this puncture. So this is the orbit of traceless n-bind matrices whose eigenvalues have maximal multiplicity. So such matrices are parameterized by choice of a vector and covector, such that covector on the vector is equal to n, up to rescaling. So if I multiply u by a number and v by inverse number, it doesn't change this matrix. So this space is a total space of affine bundle over the cotangent to Cpn minus 1. So for SUN, the minimal coadjuvant orbit is a projective space Cpn minus 1. And for the complexification, which is SLNC, there is a complexification of Cpn minus 1, which is this space. So it turns out that if you solve this equation, now on an elliptic curve with one puncture, so with one delta function here, so it means that phi will have only one pole. At this point, then the resulting phase space will be the cotangent. It will be a resolution of it will be the cotangent bundle to the space of n points on the elliptic curve with the with fixed center of mass. That's a SLN. Up to permutations, so these are unordered. And this is the simplest Hamiltonian. So the first Hamiltonian out of the sequence of Hitchens Hamiltonians. It describes a many-body system of n particles. So there is a kinetic term, usual kinetic energy, and then there is a potential term which describes a kind of repulsion between those points. But here I should say that everything is complex. So these are holomorphic. Well, it's a meromorphic function, which originally, and that was the work of my late co-author Igor Krichever. Originally, people were interested in the system when tau, when the elliptic modulus of elliptic curve was purely imaginary. In that case, you could actually restrict this holomorphic function on the real slice when z i's are real and p i's are real, and then so on this real slice, this function, this very Strauss-Pei function, will be also real, and so it will describe the many-body system of particles on the circle with the interesting potential. So Igor Krichever, 7 years before Hitchens introduced his system, he found actually the solution of what am I doing? He found the solution of this equation without solving this equation. I mean, he was not looking for solve this equation. He just found the Lux operator for the system. So something which kind of makes it explicit that it's an integrable system. And he found it as a so he was not actually interested in finite dimensional many-body systems. He was interested in the dynamics of solutions of KP equation and KdV equation. He discovered that this equation of hydrodynamics type has finite dimensional invariant subspaces. So the solutions which are parameterized by finite number of parameters which evolve in time. So one of his discoveries was that if you look at the function of the form and require that U solves the KZV equation, so with the say X. So KZV equation roughly this form. So I'm writing an ansatz for a function of X and T. But this ansatz depends on some auxiliary positions z1, zn as functions of t. So he found that if you substitute this into this equation, then the i's will move according to some finite dimensional mechanical system. And so for special value of nu, this was a system, and then he generalized. So there was some kind of indication that that these systems are integrable, they're interesting, and later the Lux operator, which Krichymer found, was identified with the Higgs field of Hitchin system, basically. So now, after this kind of little bit of detour, I want to further simplify Hitchin systems to present to you the analogs, which are defined not on Riemann surfaces, which are still complicated, but on graphs. So one real dimensional.
Before you get into the graph, like, can I ask, is it possible to define Hitchin system on Riemann surfaces with boundaries, like on annulus or generalization of that?
To some extent, but so once you introduce actual boundary as opposed to a puncture, you have an infinite dimensional phase space. So because now you cannot. So the thing is that if you look at the space of gauge fields on the surface with boundary, and you look at the way the gauge group acts on that space, it turns out that I don't remember if I discussed it here. This action is Hamiltonian, but there is I mean, you cannot perform the reduction because the moment maps, the Poisson brackets of the moment components of moment map contain now a cocycle, which is a boundary term, which has to do with the central extension of the current algebra, which becomes Kac-Moody. So if you want to perform a reduction, you have to restrict your gauge transformations to be to a rather small subgroup of on the boundary. The simplest one would be just to say that the gauge transformations on the boundary should be equal to 1. And that means that the whole gauge field on the boundary becomes invariant, and so it's an infinite dimensional space. So so in that sense, so you could define something, but it would be an infinite
So
dimensional.
the simplification is not happening.
Right.
Yeah. So one more thing. So with this Hitchin system, is it possible for someone to define something like string theory? Like instead of CFT on the worldsheet, let's say if you define Hitchin systems, is it possible to?
So Hitchin systems sit in the quasi-classical limit of a CFT. So if you study, let's say WGW theory based on the group G, and you take the limit k goes to infinity, or rather k goes to negative dual-Coxeter number, so the critical level. So these are the two limits in which you see some glimpse of Hitchin system. But really, I mean, to fully kind of embed this story into CFT and other things, you need the BPS CFT correspondence, because you actually need two parameters, epsilon 1 and epsilon 2, which I talked about on Tuesday. So yeah. So anyway, so it's a little bit of a detour. So today I wanted to talk about something elementary. So this is something which you can define. The Hitch system is not elementary in that respect. So I wanted something simpler. So so if you look at the Riemann surface from far away, and so it's Riemann surface with punctures, which actually are kind of pieces of the surface which go off to infinity. Then what you see is actually a graph. So if you look at it from far away, so it's like from string theory to particle theory. And so I want to go back to Yang-Mills theory, but now I want to replace the simple circle, which was a space manifold, by something more sophisticated, like a graph, which is I will take to be a trivalent graph. And so I will allow for this graph to have some number of tails, some number of internal vertices, and internal edges. And so this data will determine kind of the genus of this graph, which is 1 minus the first Betti number. So now I want to define my phase space to be the space of piecewise smooth gauge fields. So the gauge fields are defined on these components, one-dimensional components of my graph. Electric fields, which are functions, so they have to agree at vertices. So if I take a limit from these three sides, then they should agree. And gauge transformations are just continuous maps of the graph to the group. So then if we do the same thing we did for Yang-Mills theory, so we impose the Gauss law, which I will review later. So but on each kind of smooth component of this graph, it's the old Gauss law, which was just the covariant derivative of the electric field. So I want this to be 0. But at the vertices and the tail, something is modified. So then you will get the phase space, finite dimensional phase space of that dimensionality, which looks like the same formula as for Hitch's system, except that now everything is real. So it's a real manifold.
Does it go to identity at the tails, the end of the tails, or you allow for all?
No, they allow to act. They still allow to act.
Act on that. Okay. So you'll again get a finite dimensional phase space at the end of this. I'm just trying to relate it to the previous question where you had boundaries and then versus punctures.
This models this is the analog of the Riemann surface with punctures.
Right. So this would be just like punctures. So you allow for all gauge,
yes,
all boundary conditions for the
summations.
Right.
The fact that the gauge group does act at the puncture, that's the origin of this delta source, because that's the moment map for the. So J is the moment map for the finite dimensional group action on the quadrant orbit, but here I'm embedding this finite dimensional. So now I'm making the infinite dimensional group act on the finite dimensional object by evaluation. So then the moment map for the infinite dimensional group takes values in two forms, densities, and so this is the density which is attached to this point. So the moment map is, as I said, it's a collection of these things on intervals, on internal intervals, and on internal vertices I have the sum of 3 electric fields which come from these sides, and then so the condition is that this sum is equal to 0, and at the tail I'm just saying that this limiting value of the electric field should belong to the orbit which I specify. So then the Hamiltonians would be the functions of electric field, and so I will build these functions out of the same polynomials pk. I will be doing something like that. Then there is some count how many independent functions you will get, which I will skip for the lack of time. But it's a cute computation, which is on the face of it, it's slightly different from Costant's computation, but it should be the same. So now we can go back to the geometric interpretation of this phase space. And so what is it? So now in the case of G equals to 0, which means it's just my graph is just a tree. Trivalent tree with n tails. And so now at each tail sits the quadrant orbit of SU2, which is just a two-dimensional sphere. The spheres are characterized by one parameter, which I call nu, and so they just map to the actual real lengths of actual edges. So my phase space for this problem is just the space of polymers, whose sides are fixed, and so they considered up to rotations. Now there is a little bit of a subtlety, namely, this is not the ordering of these edges is not unique. So there is a non-trivial symplectamorphism of this phase space, which uses the same edges but rearranges them in a different order. And so that's an interesting part of has to do with the duality transformations.
So arbitrary
classically, they continuous numbers.
So there's just classical code. It's not yet quantized.
Classically, they arbitrary positive numbers. In fact, there are some inequalities for so this picture doesn't describe in general the full phase space. It describes maybe a patch on the phase space, which is singled out by some inequalities having to do with triangle inequalities. But then you can change the ordering and go to another patch of the space. So for example, in this example, so I could start with this arrangement things, but I could also change this one. So by some degenerations, you can make these configurations overlap. But there are some configurations which can only be reached in one ordering, but not in the other.
So this is like from the Riemann surface, you go to different graph S channel.
So they have to, yeah. So if you go back to the picture of the sphere with 4 punctures, so these are different degenerations. Different degenerations. In fact, these degenerations, they are interestingly in one-to-one correspondence with the ways of triangulating this n-gon by diagonals, by non-intersecting diagonals, which split them into the triangles. And so this is the this trivariant graph actually tells you how you degenerate Riemann surface of genus 0 with n punctures into the union of so these are just spheres with just 3 special points on them. Sometimes the special points are punctures, sometimes these special points are nodes of the degenerate surface. So if you don't know anything about gauge theory, but just think about polymers and think about what kind of commuting transformations, independent transformations you can do on these polymers without changing the length structure. Well, you can bend them along the diagonals. So if you bend this polymer along this diagonal or along this diagonal, you can do them independently. By bending, I literally mean those bending. And so, but remarkably, when I keep saying that this is a phase space, it's a symplectic manifold. And so there is a symplectic form which comes from the original gauge theory construction, for which a choice of Darboux coordinates is given by the lengths of those diagonals and the dihedral angles, the angles between the triangles, these diagonals. Right. So the angles in the 3-dimensional Euclidean space. And so if you look at the flow, that's why it's called origami. So, but it's one of the reasons to call this whole thing origami, but there will be another reason which will be seen later. So the flow which is generated by the length of this diagonal is precisely the bending along this diagonal. But as you can see from the example of the foregone, there are different choices. So I can bend along this diagonal, or I can bend along this diagonal. These are not commuting flows. So these will be different Darboux patches.
From the perspective of this trivalent graph, how to see this folding, how it is encoded there?
So, so this trivalent graph gives you a way of encoding the Darboux coordinates on the phase space, which I think I have. Yeah. So, so okay. So there are Darboux coordinates which I in words already introduced. They're called alpha and beta. So alphas are the lengths of diagonals, and betas are those angles. On this trivalent graph, to every internal edge of a trivalent graph, you associate a pair of coordinates, alpha and beta. And so alpha you can describe rather simply in terms of the eigenvalues of the electric field, which propagates, which sits on this edge. And the eigenvalue, because of this equation, the eigenvalue is axiom dependent. The electric field itself changes, but its eigenvalue doesn't change. You can take its value anywhere. But to describe the compute this angle beta, you need some data involving 4 edges connected to the internal edge. So this is, well, because to compute the angle, it's the angle between 2 triangles, and triangles that know about these 2 sides and these 2 sides.
So the Hitchin system on this trivalent graph knows about that.
So this
angle
what I'm saying is that this system is a kind of a tropical limit of Hitchin system.
Yes.
So Hitchin system is still complex, but you can imagine kind of squishing it in the so to make it half-dimensional and real.
Yeah.
Now, these Darboux coordinates were discovered by many people in different contexts, and depending on whether you work in Euclidean geometry, this ambient geometry doesn't have to be Euclidean. It could be spherical or hyperbolic, or it could be Minkowskian. So it could be flat but Minkowskian. So different mathematicians kept rediscovering them. Now, this is kind of a small remark that if you think about the two-dimensional Yang-Mills theory, so the thing which I started with. So so far we were discussing the structure of the phase space, but the phase space depends on what you choose as your space, as a spatial slice. And if the worldsheet of Yang-Mills theory is some two-dimensional Riemann surface, depending on whether I place my spatial slice, the space could look different. It could be 2 circles, it could be 1 circle. So two-dimensional field theory is more than just a phase space with dynamics in it. There are additional operations which tell you what happens with phase space when the space changes. So this is the picture for the pair of pants transition, where 2 circles join become 1, or other way around. So for each circle, we can attach a phase space, which was the simple space we started with. But now there is some map between the product of these 2 phase spaces into the single phase space. So this is infinity structure. And now I'm generalizing. So this simple circle is generalized to an arbitrary graph, trivalent graph with some topology. So there's more structure on those spaces. And so that gives, so that's kind of proposes that in addition to this smooth Riemann surfaces, whose spatial slices will be just circles, unions of circles, because this integrable system is interesting when you place it on general graph, I'm suggesting to study 2D Yang-Mills theory on more general world sheets, which are not smooth as two-dimensional surfaces, but whose slices will be trivariant graphs with certain number of tails. I will show you the pictures of what these graphs look like. And so they look like origamis in a different sense. So as I said so there is a version of that which will show up not in 2D Yang-Mills, but in the three-dimensional Chern-Simons theory, compactified on the circle. Then you see this similar analysis, but instead of the kind of Euclidean spaces, you will see curved spaces, three-dimensional curved spaces. With three-dimensional, if the gauge group is of rank 1, so the group is SL2R or SO12 or SO3. So what about the higher G? So this is something which has not been studied by mathematicians, but since the basic example of the phase space coming from 2D Yang-Mills theory corresponds to the circle in my nomenclature has genus 1. So there is one loop. And historically, we studied the case when we introduced one puncture, which in the language of Yang-Mills theory means that you insert the Wilson line. So maybe it's time to erase it. So by the way, where do you encounter in Yang-Mills theory this spaces associated with trees? This is if your space is just a line, so it's non-compact space, and you have some Wilson lines in some representations, R1, R2. So this is time, this is space. Let's say it goes off to infinity. So this corresponds to in this language, it will correspond to the graph which is the so-called comb type graph. So the graph will have genus 0, and the number of tails. This is k. Then I believe number of tails will be k plus 2. So these are the tails which correspond to the representations of the Wilson lines, and these guys correspond to the infinity, plus or minus infinity. So orbit-wise, so the orbits, so this will be the orbit, the trivial orbit. You want the ends to correspond to trivial orbits if you want to have finite energy, because the energy of this configuration is the integral trace b squared. And so if my integration is over all of R, and remember the Gauss law says that on the smooth part of my space, E is covariantly constant. So it means that beyond here, the electric field should vanish. Otherwise, my energy will be infinite. And also beyond here, the electric field should vanish. But now, whenever you cross this vertex, the electric field jumps. So the electric field here will be, so this is equals to 0. And here it will be equal to the element of the orbit attached to this tail. And here it will be now the sum J1 plus J2, J1 plus J2 plus J3. This is J1 plus Jk minus 1. And then here it should be, on the one hand, it's a sum of all kj's, but on the other hand, we are now going off to infinity on that side, and so it should be 0. And so that's the real analog of the constraint, the sum of the residues is equal to 0. So, so this is the simplest comp type graph. But now in CFT, people who are familiar with conformal blocks, so once this is kind of a simplest channel for conformal blocks, but then you can do all kinds of flips, duality transformation. So from this, you can go to another channel where, for example, two of these guys will split and live on a different tail. So in the language of 2D Yang-Mills theory, what it means is that now we sort of degenerate. So we fuse two. So we fuse two Wilson lines together. And typically what people do when they fuse them, they just say, okay, we just decompose the tensor product of representations and irreducibles and study Yang-Mills theory when we insert one of these irreducibles and then sum later. But I don't want to do that. I want to take this picture as a whole. And so I want to associate to this graph a different type of worldsheet. So this worldsheet will now look a bit singular because now there will be the edge kind of coming out. I think I have pictures of that. But anyway, so and then there will be my Wilson lines sitting on this edge. On the edge. It's not edge. It's kind of. In India, you have this interesting gourds, ridged gourds. I think it's called these vegetables which have ridge gourd. Yes. So this is the kind of worldsheet you will get now. So it's Yang-Mills theory on the surface of ridged gourd.
Say somehow that you are taking each channel partial waves, but now you're trying to construct partial waves which are crossing symmetric already. So this diagram be like block or partial.
Right.
But
So so in this, so maybe if we wanted to couple 2D Yang-Mills to something like 2D gravity, then we would have to sum over a class of topologies of a worldsheet, and so that would probably enforce this crossing symmetry. And so then we would be summing over different types of the worldsheet. But right now, I just want to generalize the individual kind of instances of this of this sum, and I'm arguing that I need to enlarge the class of worldsheets for which this theory should make sense. Okay, but but historically, so what happened was that if you don't study Yang-Mills on the infinite line, but you compactify it on a circle, then because now this integral is over finite space, the electric field doesn't have to vanish here. But since this is periodic, so now the eigenvalue of electric field which starts here should be the same as the eigenvalue of electric field which comes back here. So even if you have only one Wilson line, so this is space. Remember, this is space. Now this is space-time. And I just have one Wilson line. So what it means? It means that so my graph has this structure. So now the gauge field may have a non-trivial holonomy around the circle because they have a circle. So I think I wrote it somewhere. Yes. So this gauge field will have its holonomy will have an eigenvalue, which is e to the I phi or e to the minus I phi or e to the minus I phi, maybe over 2. And the electric field will necessarily be non-abelian. So if I can go to the gauge where the gauge field is abelian, So A belongs to some subgroup of SU2. So this is along the Z direction. The electric field will have to have a non-abelian part. So because the electric field has to jump, but the jump is such that the eigenvalues should agree. So it's an interesting condition, which I will make geometric later. So when you compute the resulting value of the Hamiltonian, then in the variables which are the eigenvalue of the gauge field and the kind of a zero mode of electric field, the Hamiltonian has this form, and that's a two-body version of the Hamiltonian I wrote previously for the many-body system, except that instead of the elliptic function, here I have its trigonometric version. So this is this repulsive potential, and this is the kinetic term. This is the center of, so this is the relative motion of two particles which live on a line, on a circle, which repel each other with inverse sine square potential. But it can also be, but I can also go to the to another gauge, the gauge where the electric field is diagonal, and so its eigenvalue will be equal to alpha. So then this whole thing will be just alpha squared, or 1/2 alpha squared. And it will be kind of a variable, conjugate variable to alpha, which I call beta, which is the angle variable. So this action and angle variable. And now the question is, how can we do? What is the geometry of this? So previously, in the genus 0 examples, we had these polymers as representing the gauge equivalence classes of my configurations of electric field, magnetic field, and the gauge field. So now we need to try to cook up something which will resemble that story, but now allow for loops in my graph. So if I look locally at this graph near the vertex, well, I have a trivalent vertex. And so if I follow the rules of associating polymers to trivalent graphs, well, I would associate a triangle, this vertex. One side of this triangle is fixed, is this parameter nu, something which comes from the Wilson loop, Wilson line, sorry. And these other two sides, which are equal, these are the eigenvalues of the electric field. But where is the room for beta? So how can I need to have some kind of bending angle. And what is the role of phi, the eigenvalue of the gauge field? So what's there to bend and how to see the dynamics? So the idea is first is that, okay, so I have a triangle, I need an angle beta at the edge connecting two triangles. So, okay, let me just replicate this triangle at the angle beta. And so since nothing stops me from continuing, so I will just, take the universal cover of that graph. I will get the infinite version of that graph. And just try to associate a polymer to this infinite graph. So infinite comb type graph. So I will just keep bending at the same angle beta. So we'll get some kind of a repeating structure. But so still not quite rigid. I want to see some rigidity. And so the idea is to say that this infinite structure is actually finite if I introduce a conical deficit angle on R3. And this conical deficit angle, so the angle will be phi, will be the parameter of the gauge field. And it's also, so you also need to know where to place this third vertex of a triangle. So two vertices were taken up by the edge, which we knew we had to introduce because it had the length nu, which was the part of the orbit, the tail data. But the third vertex has to be placed somewhere. And so this position is it's actually a modulus of the problem. I call it a bead. So the geometry, therefore, is the following: that you take the three-dimensional Euclidean space, you introduce a cosmic string in the sense of three-dimensional gravity. So it could be like a trajectory of a massive particle. So what massive particles do, they create a conical angle, conical deficit. The amount of this deficit in three-dimensional gravity is determined by the mass of the particle. So here it will be just my parameter phi. But then somewhere along this infinite line, which Vishnu and Brahma were arguing about, there is actual origin, which is where they all three of them met. And so I placed the bead there. So this is the bead. This is where the invisible vertex of this of the triangles is allowed to be placed. So it's some kind of black hole. We don't see it. So these are the pictures which I generated using Mathematica. So this angle doesn't have to be rational. If it's rational, then you get an interesting, nice picture. If it's irrational, well, you just keep repeating. But it's just a feature of the space-time with the irrational conical deficit. Have infinitely many kind of reflections. So there are kind of two angles in the game now, but which are actually related, which are not independent. So one angle is the feature of this cosmic string. So it's the defect. Now the question is the following. So suppose you live in space-time with this conical defect, and you have a rod of length nu. The length of the rod is fixed. So now you want to say, but I want to have a closed polymer.
Right.
What does it mean to be closed? Closed means that, of course, without a conical defect, well, if you have just a rod, the rod has two ends. But with the defect, it might be that those two ends are actually this. It's one point. If you take into account that when you cross the defect, so this is actually it's actually 1 point.
Right.
Depending on which chart you look at this space with conical singularity, so in one chart it looks like a straight line in Euclidean geometry. On the other hand, if this is exactly so the part of the space which I cut out by scissors to create a conical defect, there is some distance from the from this origin. So this is my cosmic string is perpendicular, where I can place this rod so that these two ends will be precisely the same point.
Correct.
So it's a closed one gon.
Right.
So in usual Euclidean space, we need at least 3 rods to have something closed, to make something closed. But if you have a conical singularity, sometimes you can do with just one. Now, so knowing phi and nu, so there is 1 degree of freedom remaining, which is this p, which is where on this rod this third vertex is placed. So maybe I'll draw it this way. So this is the bead. So there is this plane which is perpendicular to this cosmic string, which contains this rod. So this rod will have so the rod has to be, it's a little elementary geometry. So this rod has to be on the 2-dimensional plane, which is perpendicular to the cosmic string. But the distance between this plane and this bead is a free parameter. So this is which turns out to be canonically conjugate to the deficit angle. And now the beta, so this is the angle. I hope I show it on the next. Oh, no, I didn't show it. So this beta, well, it's the angle between, so this is this triangle, right? But now, because of the conical, so deficit, it's like a mirror, so there is a reflection, so I can compute, I can place the similar triangle next to it, and there is some specific angle which separates those triangles, which we can compute. And this is the elementary geometry computation. But then it turns out that this variable is canonically conjugate to this variable, and this whole thing can be viewed as a Hamiltonian. So cosine of phi over 2 is a Hamiltonian, different Hamiltonian, on the same phase space, such that it is expressed in terms of the coordinate of the original Hamiltonian, and the action variable for the original Hamiltonian is the coordinate for the new Hamiltonian. So there is some kind of duality which I studied with Fogorsky and Rubtsov many years ago, which in this case is a duality between Sutherland and rational Resonance-Schneider models. You all know this duality in its quantum form. What is this duality in quantum form? If you quantize this Hamiltonian using phi as a coordinate and p as momentum, its eigenfunctions are Legendre polynomials. I mean, okay, if nu is quantized, it will be conventional Legendre polynomials. If nu is not quantized, this will be Legendre functions. Now, Legendre polynomials, so they obey two kinds of equations. On the one hand, there is a differential equation, which is this essentially Schrödinger equation. On the other hand, they form the orthogonal system of functions. So if you multiply the Legendre polynomial by, let's say, by cosine, so Legendre polynomial of phi as an argument phi. If you multiply it by cosine of phi over 2, you will get something which you can expand on the linear basis of those polynomials. So this equation, you can view it as a recursion relation, which is used in matrix models, but you can also view this recursion relation as a quantization of another Hamiltonian in which, so now look at this function of alpha and beta. Alpha and beta are canonically conjugate, but now if I quantize beta as d by d alpha, this Hamiltonian becomes a difference operator now. And so this difference operator is the recursion relation. So this is the beginning of some kind of duality story. Okay, so for general gamma, the phase space, if you look at the dimension, in addition to the space of closed n-bond polymers on R3, contains also 6 times G parameters. So for each genus, you have 6 parameters. And so what the 6 are, these 6 describe a choice of a cosmic string, a choice of the bead on the string, and the choice of the deficit angle. So a choice of the cosmic string is a choice, is a position of a straight line in three-dimensional Euclidean space. So straight line has 4 parameters, 2 for the orientation, and 2 for the kind of position in the plane transfers to this orientation. And now I'm adding 2 more parameters, which is the center and the deficit angle, so kind of the mass of the particle which moves. So that's the proposal for the interpretation of the phase space for these general graphs. And so then the triangulation, so now the vertices of triangulation, the internal vertices of triangulation should be at the beats. Now,
so Nikita, if you have 2 cosmic strings,
yes.
Like,
So
what happens if they intersect and so on? Like, will it be? I mean, that's unlikely in 3D.
Yeah, that's unlikely, but I think it's allowed. Yeah, I think there is no.
Then this polymer thing.
Yeah. No, the
nice.
actual structure of space is very complicated because you see the thing is that so each cosmic string defines what is called a kaleidoscope or labyrinth. So there's some rotation around it which we identify the space by. But now if you have 2 of them, these are non-commuting rotations. So they define something very complex, very complicated. So it's not a pleasant space to look at, but locally it's just flat space.
Right.
So there are interesting duality transformations which correspond to those flips. And so if you, instead of flipping in this diagonal, you start flipping across that diagonal. And there are interesting canonical transformations which relate different systems of Darboux coordinates. So, I mean, I didn't talk about this in detail yesterday, but I mentioned the generating functions of Lagrangian submanifolds, and there are generating functions of simple ectomorphisms. So if you have two systems of Darboux coordinates and map between them, this map can be described using a generating function, which will be a function of, let's say, a coordinate, the original coordinate and the future coordinate, and then you compute the original momentum and the future momentum as derivatives of this generating function. So this picture suggests that this generating function has something to do with tetrahedron, whose size lengths are given by all these alphas. So there are 4 alphas which sit on the outer edges, and there is alpha which is on the internal edge, and then the flipped internal edge. So there's some kind of geometric quantity which you associate to a tetrahedron. And so the naive guess would be that it should be the volume, but it turns out not to be the case. It will be the volume in the hyperbolic case or in the spherical case, but in the Euclidean case, it's an interesting invariant which you can associate to the. Say again? What's your confusion? Yeah, so 6G symbol is a volume actually. So it's like so this is a kind of expand. So you need to take a 6J symbol and expand in the powers of cosmological constant or inverse radius of curvature, and so you need to. So the volume, you see, the reason why the volume wouldn't work is that in Euclidean geometry, alphas are lengths, so they're measured in centimeters, but betas are angles, so they're dimensionless. So for this formula to make sense, this quantity S has to be measured in centimeters. So it should scale linearly with size, not cubically with size. But that gives a way to. So there's a hint. So it turns out not many people know that. So everybody knows the following fact, that if you take a tetrahedron in hyperbolic space, there are the so-called Shapley relations, Shapley formulas, which say that the derivative of the volume of the tetrahedron with respect to the length of its edges gives you the dihedral angle between the faces, which are shared by this edge. But it turns out that there exists a similar function for the volume of Euclidean tetrahedron. So something whose derivative with respect to the edge length gives you the angle. But this function doesn't have a good name because it's not a volume. It's linear in the size, but its expression in terms of the length so involves logarithms so you can get it by taking the volume of hyperbolic tetrahedron and expanding in the inverse powers of curvature and looking at the 1 over r term. So the volume will be 1 over r cubed term, and you take so you use a subleading term. And so there is such a function. So these are some formulas you can. So this function, the function is expressed actually in a simple way, just the sum of alpha betas, where betas are computed by, school, maybe not primary school, but primary school stereometry. This is actually related. So this is an interesting story of I don't remember which was like a second or third Hilbert's problem. So Hilbert, in his list of problems, formulated the question: if you have a polytope in 3 dimensions and you chop it up in pieces and reassemble, so what are the invariants? So so if I have 2 polytopes, is there a way to reassemble them? Volume is one of the invariants, of course, but there is a second invariant, which is called Dane invariant, which takes values in a sophisticated space. And it's essentially the sum over all edges, the tensor product of the length of the edge times the angle. So that quantity turns out, if you chop this into pieces, this quantity is invariant. Right? And so this generating function is some kind of a contraction. So if you instead of tensor product, you take the ordinary product. So this is sometimes called a symbol in the theory of polylogarithms. It's a symbol map. Okay. So Now, when you work in higher genus, you don't have to actually have tails, as Hitchin in original Hitchin's case. For example, you can have a look at the genus 2 case, and so you can get something which exists without any tails. So you have some kind of a polymer without rods, actually, but it's a structure which. So this is an example of 2 cosmic strings, which I think I chose to be not intersecting, but I don't know. Maybe if they intersect, there is some degeneration here. Okay, so then maybe there are other generalizations. So maybe there is some, so Fermi worldsheet. So maybe there is some kind of connection to, what is it that people in loop quantum gravity study? They study spin foams, I think. Yeah, so maybe there is some connection. Okay. Then in addition to evolution Hamiltonians, we can also add those graph transformations. Oh yes, these are pictures which I engineered using Mathematica. There's some transformations. Thank you.
Thanks a lot.
So you went over that.
Yeah. Before anyone asks, I want to ask something. So if I quantize this the phase space,
Yes.
Is it possible for me to think of these edges, like the endpoints of the graph,
Yes.
as some sort of states, and can I think of it like a scattering process?
Right. So this is, of course, I mean, this graph, the same graph we encounter in conformal field theory in labeling conformal blocks. So there, so with some kind of fusion. So it describes some kind of fusion process.
Yeah. So seeing this, like, I get a feeling that if we know how to introduce gravity, 2-dimensional gravity, and then in your limit, this will be like gravity on a line.
Right.
And then it's more like studying the field theory limit of string theory. And then it seems like whatever you get, those formulas may be somehow related to this positive geometry and amplitude and these people are doing.
Yeah. So yeah, that's one of the motivations. So this tropical, the tropical limits. So there is something which we study in conformal field theory, but it's what I described is probably some kind of alpha prime to 0 limit.
Yeah.
It's not the conventional limit. Which,
All these origami, everything is in R3, not in the Mandel's name.
No, and then the point is that
well, it's
maybe
spin space. So R3 is R3 showed up because of the group being SU2, right? So it is some kind of kinematic. Well, so
it seems like very much.
I mean, it could be related. It's not that far.
Yeah.
Yes.
By being erratic.
Yes.
You mean that it is 2 pi is not a multiple of pi?
No, this so what the rationalized is a ratio of 5 to 2 pi.
Okay.
Yeah.
Any more questions? Online?
I have a very quick question. So you started to talk with this complex integrable system.
Yes.
And somehow when you when you reached the gauge origami part, everything became real. I just want to understand how. Yeah. So is one a sub case of the other, or is it a special case, or yeah?
Yeah, I think so. If you took Hitchin system and literally degenerated the underlying Riemann surface so that so you collapsed all handles. But then you also impose some reality condition on spins, like on residues. So you had 2 things: you degenerate and then you restrict. You restrict the initial conditions. So then become this.
I see. Thanks.
Okay, so if there are no more questions, like let's thank Nikita for this wonderful